Hello everyone, good morning. It is a pleasure being with you today. I'm Rebecca Salles and I'm a PhD student at CEFET-RJ. So this presentation introduces Harbinger, a framework for integration and analysis of methods for event detection in time series. Let us begin by defining a time series as a sequence of observations of a particular phenomenon of interest that is collected over time. Often it is possible to observe significant changes in the behavior of the observations of a time series, and these changes frequently characterize the occurrence of events. This example shows a point in time when the occurrence of an event causes a change in the trend of the time series of global temperatures. So generally, the occurrence of an event can be detected by the observation of outliers or anomalies, points of change in behavior, and or frequent patterns or motifs. So an anomaly is a pattern or an observation that deviates so much from the other observations as if it was generated by a whole different mechanism. And anomalies refer to a special kind of outlier. Particularly, it is an outlier that is of interest to an analyst. Change point, on the other hand, it is a point in time or a time interval that marks a significant change in the behavior of a time series. And change points separate different states of the process that generates the time series. This example shows segments of a time series observations that seem to be generated by the same process, and these segments are separated by red vertical lines representing the change points. Finally, an event may appear as an unknown specific pattern that occurs a significant number of times in a time series. In that case, it is called a motif. So as it happens in a particular domain application, an event can represent a phenomenon with a clearly defined meaning. And in that case, the problem of detecting such events becomes relevant, especially for applications based on sensor data analysis, for example. In fact, event detection is recognized as a basic function in surveillance and monitoring systems. And within the problem of event detection, we can specify anomaly detection as the problem of finding an unexpected behavior, that is, deviations from trends, volatility, etc. And change point detection, we can define it as the problem of finding behavior change points. And this problem is directly related to finding concept drifts in time series. And we can specify motif detection as the problem of identifying frequent unknown patterns in time series. So, the literature presents several methods for detecting events. We'll call them detectors from now on. And for the automation of the detection process, it is essential to adopt a highly reliable method. However, different detectors can perform differently in different environments. Since all the algorithms approach the problem differently and can work on exclusive subsets or transformations of input data, there is no single algorithm that is optimal in all situations. So the choice of a suitable method for a time series is for sure not a simple task. The selection and parameterization of a method are directly related to the initial assumptions that you make about the behavior and the assumptions that you make about the statistical properties of the data. And the complexity of this task is even aggravated, considering that the actual nature of the events observed in a time series is often not known in advance. In this case, a method specialized in detecting a certain type of event may disregard the occurrence of another type or even misidentify them. For example, anomaly detection alone may not know if new values are noise or anomalies in trend or in volatility or even perhaps change points. So the proper selection of a detection method can lead to failure to identify time series events, and in turn, failure in event detection can affect decision making or lead to false positives. And with this, there is a loss of credibility, for sure, in the use of control techniques and possible damage to applications. To address this issue, the literature actually presents a number of frameworks that allow the application of different detection methods. Unfortunately, though, they generally specialize in detecting events of a specific semantic. There are a number of frameworks, particularly that are specialized in anomaly detection, for example. Such specialized frameworks may miss or misinterpret events of different types contained in the data. Moreover, they are commonly highly dependent on the limited number of detection methods that they implement. And with this, there is currently a demand for a flexible framework for the integration and the analysis of different event detection methods. Such frameworks should allow the identification of different types of events, as well as the combination of different personalized detection methods. And furthermore, it should enable a comparative analysis of their detections. So this work aims precisely to meet these demands. With this work, we have developed Harbinger, a framework for the integration and analysis of event detection methods. For this, some of the main methods for detecting events available in the literature are standardized and integrated. And new customized detection methods can also be included by the user. So such integration enables a qualitative and quantitative comparative analysis of its detections, as well as the combined use of the methods so as to characterize the detected events in a more assertive way. Provenance can also be achieved by model lifecycle management systems. And the Harbinger was experimentally evaluated based on synthetic and real data, and it was found that its features actually help to guide the choice of appropriate detection methods for a given time series, and also contribute to the understanding of the semantics of the detected events. So the general structure of Harbinger is illustrated here, being formed by 4 main functionality modules regarding event detection, in blue, detection quality evaluation, in green, combination of detection results, in orange, and comparison of detection performances, in purple. So basically, the process of using Harbinger initially includes the instantiation of an event detection process. This detection process is implemented by the first 2 modules illustrated in the diagram. And for this, we pass as input a set of time series, the implementation of a particular detection method, and its required parameters. Also, for assessing detection quality, we should pass a list of respective real events that were previously classified, and a selected metric to assess detection quality. And after running this instantiation from the first module, Harbinger returns a set of detected events, here represented as this EJ symbol. And the optimization of the method's parameters is also allowed. And then the quality of the detections are evaluated by the given metric, using the given real events as basis for comparison. And this value is then used for the quantitative analysis of the detection quality. And in addition, Harbinger generates a plot that can be used for a qualitative analysis of the detections. Harbinger is also designed to allow the combination of the results of a set of instances of the detection process. This is done by the combination module that joins the sets of events detected in each instance, and consequently the resulting union set may encompass detected events of different types presenting different semantics, and these semantics are identified according to the particular methodology of their respective detection methods. Finally, the comparison module ranks the quality of the detections based on the computed metrics, and event detection performances can then be ranked accordingly. And this rank guides the choice of detection methods that are most suitable for a given application. And ultimately, it is important to mention that all of these parameters and produced artifacts can be recorded in a model lifecycle management system so as to ensure provenance of the results. Harbinger was developed in R, and it provides a library of functions that implements the functionality modules described previously. And the framework allows the user to define custom event detection methods, so it is not limited to a certain fixed number of pre-implemented methods. And also it allows parameter optimization based on grid search approach. Moreover, Harbinger provides the implementation of several methods for detecting events that are currently available in literature. And among them, there are methods for detecting anomalies of trends, anomalies of volatility, and change points. Also, in order to facilitate the evaluation process, Harbinger includes the implementation of the main metrics that are used to assess the quality of event detection. More details about the Harbinger are available on its dedicated page that you can see here, where you can find the actual code of Harbinger and how to use the framework. So Harbinger was submitted to an experimental evaluation in order to analyze the contributions of its functionality modules. For this purpose, a synthetic non-stationary time series was built in order to highlight the behavior changes of a time series. And we also adopt two real data sets that are commonly used as reference to assess the quality of the event detection methods. Namely, we have the dataset created for the Gecko Challenge of 2018 with variables of water quality, and the dataset provided by Yahoo Labs with variables of traffic in the Yahoo services. Both these two datasets contain previously identified events. And event detection processes were instantiated for each of the selected time series. For this, we adopted 7 detection methods covering events of different types, namely trend and volatility anomalies and change points. The quantitative assessment of the quality of the detections is based on confusion matrices and the F1 metric, while the qualitative assessment is based on visual analysis of the produced plots. So to assess the event detection and the combination modules, we use the non-stationary synthetic time series that we have built. The first plot here shows red dot markings corresponding to trend anomalies that were detected by a given method A that specializes precisely in detecting this type of event. Trend anomalies can also be observed in the second plot that shows the detections by a different given method B, and this last method, however, is also able to detect change points, represented by these dashed vertical lines showing sudden changes in behavior. It follows that the detected change points actually tend to demarcate the actual non-stationary subsequences of the series that we were expecting. And when comparing the results, it is possible to observe some coincident detections despite adopting different approaches of these two methods. And we can argue here that the first method was in fact able to detect some change points that may have been erroneously identified as anomalies. In this case, the analysis of the second method's results contributes to a better understanding of the nature of the events detected by the first one. And the same can be said about when comparing the detections of the second method with those produced by the method C, for example, that specializes in detecting volatility anomalies, here represented as red triangle markings. So similarly, the analysis of the latter results makes it possible to understand that the agglomerated set of change points detected by method B around the observation 750 may actually be volatility anomalies instead of change points. So in fact, we may consider here that the methods presented are complementary. So this indicates a demand for combining the results of different event detection methods. And this combination aims to unify relevant information about the detected events that can be compartmentalized by the application and isolated analysis of the results of each detection method or of a limited number of methods. So Harbinger meets this demand by making use of its combination module, whose result can be seen here. In this plot, we can observe all the events detected by the adopted methods, as well as their respective semantics, and all of this in a unified way. So to assess Harbinger's evaluation and comparison modules, we selected the Gecko and Yahoo datasets. The following table presents results produced by the detection quality evaluation module using different metrics. Here we have true positives, false positives, F1, precision, and recall, namely. So the results correspond to detections over the Gecko dataset variables, having the parameters of the adopted method defined both manually and by optimization. Generally, it is necessary to balance and analyze different metrics to assess the detection quality more comprehensively. So the Harbinger evaluation module facilitates this analysis, allowing the different metrics to be passed as input and computed. So here, as expected, the parameter optimization resulted in higher F1 metrics and lower false positives, which means more accurate event detections. Even so, the quantitative assessment of event detections using quality metrics may perhaps be insufficient to understand the actual potential of a detection method. In this case, qualitative evaluation by graphical visualization can contribute, bringing a different and complementary perspective. So the Harbinger evaluation module enables a qualitative evaluation by producing plots, such as the ones presented here. They show events detected in a variable of the Gecko dataset with parameters defined manually and by optimization. Again, red markings indicate detected events. And in addition, real events are marked in blue, and the coincidence between the detected event and the real event is shown in green. So analyzing the first plot together with its respective metrics in the table we just saw, we have that the number of events detected with manual parameterization represents a perfect recall. That means all the events contained in the data were in fact detected. And however, the manual definition of parameters resulted in a relatively large number of false positives. Even so, we can see that the false positives are found mainly around the real events, indicating that the adopted method is sensitive not only to changes in behavior, but also to its inertial effects. And on the other hand, based on the second plot, we observed that in fact the optimization of the parameters resulted in greater precision and a lower number of false positives. However, though, not all events have been in fact detected. And that could be a problem depending on the application that you have in hand. So, also stated before, this choice of the most appropriate event detection method for a time series can be a challenge. So this indicates a demand for a comparative analysis of the results of different methods of event detection. And Harbinger meets this demand by using its comparison module, whose result can be seen in this table. what we see here is a comparison of F1 metrics for event detections produced by different methods. And we can observe in a unified way the performances of the selected methods over the time series contained in the Gecko and Yahoo datasets. An analysis of this table showed, for example, that for the Gecko dataset, the methods specialized in detecting trend anomalies presented the best performances. In this case, methods specialized in other types of events may perhaps not be the most suitable. Also, for the Yahoo A1 dataset, better detection performances were obtained by methods that are in fact specialized in detecting different types of events, suggesting that they can be perhaps complementary. Well, now we can make some final remarks. So we presented Harbinger, a framework for the integration and analysis of event detection methods. It was evaluated based on 3 data sets of synthetic and real data. And it was found that Harbinger helps to understand the nature of the detected events, as well as provides a comprehensive and unified view of the detections of different methods combined in order to avoid problems such as the disregard or erroneous identification of events that in turn could perhaps harm applications that depend on event monitoring. And in addition, the results suggest that Harbinger is able not only to assist in the choice and application of suitable methods to a certain data set and application, but also it is able to indicate the need to combine the detection of a particular set of detection methods. So here are some references used in this work, should you be interested. And that's it. Thank you very much for your attention.